Dr. Dmitry Dirin from ETH Zurich Chemistry Department from Switzerland. The title of the talk is Defect Tolerance allows unusual synthetic approaches to the lead halide perovskite nanocrystals. Okay.
Hello, everyone. I hope you can hear me.
Yes.
Okay. And can you see my presentation in a full screen mode now?
Yes, I can.
Yes, good. First of all, I would like to thank organizers for inviting me to this conference. It's my pleasure to present some of my results on this conference. I will talk today about the unusual approaches, synthetic approaches to lead halide perovskite nanocrystals. And this work has been done in a group of Professor Maxim Kovalenko. So some of you probably have heard already about those materials, lead halide perovskites. Over the last several years, there was kind of a boom of research in many different fields of chemistry. So this boom has started initially in the field of photovoltaics. Then people realized that very efficient solar cells can be prepared with lead halide perovskites, initially methylammonium lead iodide. And later from I hope you can see my pointer. So over the last several years, namely 8 years, the efficiency of those photovoltaic solar cells based on methylammonium lead iodide or analogous materials increased from above around 10% to 25% now. The second boom of research was initialized actually by our work, by the work.
I cannot see your pointer.
Yes, I think now it should work. So in 2015, group of Professor Maxim Kovalenko proposed a synthesis of nanocrystals of these compounds, namely cesium lead halides in this case. And we have shown that those nanocrystals can be very bright without any additional treatment and without shelling, which is quite unusual for colloidal semiconductor nanoparticles, as I will discuss in the next slide. And then a bit later, again, in our group, we tried to approach to study those materials from a very different angle. Instead of making colloidal nanoparticles, we tried to grow bulk single crystals of those materials via solution process. And we have shown that those materials can be very interesting for hard radiation detection. There are many other fields of applications where those materials now show some good performance. And what is important for all those fields? So those lead halide perovskite materials have several rather unique properties, but one of the most important is so-called defect tolerance. And this is important to discuss in the beginning of my talk. So in conventional semiconductors, the bottom of conduction band and the top of valence band are formed by antibonding and bonding orbitals, respectively. And typically, all defects, intrinsic defects, related to, for example, to dangling bonds or interstitial atoms or to vacancies will create a deep or shallow states within the band gap. And then this means that, for example, dangling bonds on the surface of conventional semiconductor will create traps. And this material, for example, it's unlikely that it will show exhibit bright luminescence, photoluminescence at room temperature. But we can imagine a hypothetical case. Then the top of the valence band is formed by antibonding orbital, and the bottom of conduction band is formed by bonding orbitals. In this case, vacancies or dangling bonds will not create trapped states within the band gap. And in 2015, it was shown that methylammonium lead iodide and in general lead halide perovskites represent such a case, at least partially. And in this case, the top of the valence band is formed by hybridized orbitals of antibonding orbitals.
I'm sorry. Sorry, Professor Dirin, and we've been had problems with internet connection for the last about 2 minutes. So I guess we missed a part of your talk.
Can you please repeat from the beginning of this slide?
Okay. Yeah, I hope if now it works, right?
Yes.
Yeah, now it works. We're sorry
Good.
about
Good.
the connection troubles.
Yep. Okay, good. I will try to quickly summarize what I wanted to discuss on this slide. So in the conventional semiconductors, we have top of the valence band and bottom of conduction band are formed by bonding and antibonding orbitals correspondingly. And then it means that dangling bonds and vacancies in conventional semiconductors will create deep or shallow traps. And then this material, if it has as usually we always have some dangling bonds on the surface, then this material cannot exhibit bright photoluminescence because of these trap states. But at the same time, we can imagine a hypothetical case. Then top of the valence band and bottom of conduction band are formed by antibonding and bonding orbitals, respectively. In this case, all most of intrinsic defects, such as vacancies or dangling bonds, will not create trap states within the band gap. They will create states only within the valence band and conduction band only. And in 2015, it was shown that lead halide perovskites represent this case, at least partially, because valence band and conduction band in this case are formed by different hybridized orbitals. So top of the valence band is formed by antibonding orbital of iodine and lead, and the bottom of conduction band is formed by still antibonding orbital of lead and iodine, but due to some spin orbit coupling effects, the bottom of this band is quite low energetically, and this means that dangling bonds of both lead and iodine or vacancies of lead and iodine will not create deep trap states. They create only shallow states. And this can explain the very good performance of those materials in all those different fields of research which I have been discussing on the previous slide. Because this means that the good long lifetime of carriers, it means that carriers can have very good mobility. And if we are talking about nanoparticles, it means that surface states, or namely dangling bonds, are not so crucial anymore. And here I would like to switch for a short time to the history of colloidal quantum dots, colloidal nanoparticles, semiconductor nanoparticles. For conventional semiconductors like cadmium selenide, it took about 40 years to develop a reliable colloidal synthesis of those nanomaterials, which would allow to obtain very bright particles with near unity photoluminescence quantum yield, with good control over PL peak position, so maybe color, and full width at half maximum of this emission, which is important for color purity. And knowing all this history, we can summarize that two very important parts of this research, two very crucial things to make bright colloidal semiconductor nanoparticles is surface coverage, so a good passivation of surface states, because if we remove number of ligands on the surface, then quantum yield also quickly goes down. And second important thing is if we want to make really bright particles, then we need to make core shell structures. When we are talking about conventional semiconductors like cadmium selenide based, again for the same reason, because we need to passivate surface states on our optically active core, and we also need to isolate all possible defects from this optically active core. So as I mentioned already, because of defect tolerance for lead halide perovskites, this is not crucial anymore. It looks like there were some indications that dangling bonds are not quenching emission. But we wanted to check this experimentally because this was just indirect indication and this was predicted by computation, but we wanted to check this in experiment, and there is a very nice model system for that. For a long time, there was there were attempts to grow nanoparticles inside Mesoporous channels of, for example, in Mesoporous silica. This is at a first glance, this is an ideal matrix to grow nanoparticles, because then you can have very monodispersed nanoparticles. But in case of cadmium selenide and many other conventional semiconductors, people could grow nanoparticles but never achieved any good emission, because nanoparticles in this case have a lot of dangling bonds. Their surface is not passivated at all. And now, if we believe that in case of perovskite materials, it's not a problem, then we should reconsider this synthesis. And this is what we did some time ago. And here I show you just a photo. And here I want to emphasize that this material here has no organics at all. This is just fully inorganic cesium lead bromide nanoparticles in Mesoporous channels of silica. This works for different colors. And so let's discuss in a bit more details how does it look like. So here we have electron microscopy images of this Mesoporous silica, and then if impregnated with cesium lead bromide, or in this case it's cesium lead iodide, then we can see nice nanoparticles nicely arranged in those channels. And then we also can see from another direction, and we see that not all channels are filled with this material, but at least nanoparticles are nicely isolated from each other. And from ETH measurements, we can see cesium lead iodide. So we can measure, as usually, we can measure distance between nanoparticles. We can show that size of those nanoparticles is what we expect if for these channels. We can, as usual for semiconductor nanoparticles, we can tune size of nanoparticles, and therefore we can tune peak photoluminescence peak position by tuning the size of nanoparticles if we use different, so Mesoporous silica with different size of channels. And also what is more unique to lead halide perovskites, we can tune color by tuning composition. So for cesium lead iodide, we will have red emission. For cesium lead bromide, it will be green to cyan emission. We also can tune A cation instead of cesium, we can use methylammonium or formamidinium. So here is the summary of the previous slide, just to show that we can tune size by both composition and size. So we can tune PL maximum by composition and size. And also that we are not limited to pure compositions like cesium lead bromide and cesium lead iodide. We can also make a mixed cesium lead bromide iodide. It's similar to colloidal lead halide perovskite nanoparticles, which we have shown before, but here we show that it works also in mesoporous. Then we use synthesis in mesoporous silica. Since we use mesoporous silica, we have quite big microparticles, and in order to make them more processable, we wanted to try to transfer this material to this to disperse better this solution, and we show that if we use micro balls of this mesoporous silica of about 200 nanometer in size, and we use sodium docusate, so it's abbreviated here as AOD, we can disperse those micro balls impregnated with nanoparticles of cesium lead bromide in toluene. And we wanted to use toluene because lead halide perovskites, as many other halides, are very sensitive and very well soluble in water. So in this case, we prefer anhydrous, anhydrous and non-polar solvents. This study already have shown us that indeed those materials can be bright even in the presence of surface states and even in the presence of dangling bonds. So this means that this explains why we don't really need a shell around those materials to make them bright emitting. But a shell could still help to make those materials more stable. Because as I mentioned just a moment ago, those materials are very sensitive to moisture, and so shell can protect them from the moisture, could protect. But those materials are very ionic, and it's very difficult to grow shell around those materials. It turns out to be much more difficult than in the case of conventional semiconductors. And from another hand, if we know that we are not limited by the dangling bonds, then we can consider a very unusual synthetic approach to shelling of those nanoparticles. So we can talk about so-called uncored nanoparticles. In the case of colloidal nanoparticles, if we start to shell, as I mentioned just before, if we want to shell them, we always have to apply some polar species because we want to uncore them, to bind them to the shell. And since those nanoparticles have very dynamic surface, they, in the presence of polar species, they lose ligands and then they start to merge and lose luminescence. And we now want to uncore those nanoparticles to optically inert carrier, which would not allow those nanoparticles to merge. And then in the presence of polar species, we can try to shell without merging. If you're from the field of colloidal nanoparticles, you can immediately say that there are several issues. So first of all, in this case, we don't have heterogeneous, so we don't have burst nucleation, homogeneous nucleation. We will have to work with heterogeneous nucleation, and usually for colloidal nanoparticles, it's a big problem because you will have very polydispersed nanoparticles, and then if you have polydispersed nanoparticles, you have very broad luminescence peak. But in case of perovskites, it turns out to be, again, not critical because we are working now in a weak confinement regime, and even broad size distribution will not induce the broad photoluminescence peak. So second potential problem is non-epitaxial interface, but again, there is a chance that if we find the proper substrate here, proper carrier, then it will be not a problem because, as we know from the first part of my talk, some intrinsic defects are not creating traps within the band gap. And third problem, which you may anticipate, is light scattering, because now we have big carriers, which probably will scatter light. But this is a problem only at the first glance. In reality, the main anticipated application for this type of material is in display application, so the luminescent material. And in displays, actually, people even add on purpose some scattering centers to improve haze of those displays. So, and how we do this synthesis? First create conditions in which we have first nucleation of our carrier. In this case, it's KBr, and then a heterogeneous nucleation of cesium lead bromide on the surface of carrier. Then those nanoparticles already cannot merge, and at this point, it's fully inorganic system. We don't have any ligands. And then on the second step, because nanoparticles are merged and uncored and they don't merge, we can try to attempt a shelling with sodium docosate and didodecyl dimethyl ammonium bromide, which in toluene precipitate in the form of sodium bromide and then create a shell of sodium bromide around nanoparticles. But let's go step by step. So on the first step, we already can see a fully inorganic material. So again, our nanoparticles are not passivated by any ligands, but they exhibit a bright emission. And for comparison, here I show you a photo of just cesium lead bromide. No emission at all, as you can see here, and it's a different color. If we look in a confocal microscope, we can see microcrystals, nicely faceted, and the habit is typical for KBr, for sodium bromide or KBr. If we look in electron microscopy images, we can see that those nanoparticles are, we do have nanoparticles which are mainly localized on the surface of those carriers. I will go very quickly now for those results. We still can tune, as usual, we can tune PL peak position by tuning composition of those materials. We also can tune by size of nanoparticles. But what is more important that we can make, we have an optimal range of cesium lead bromide to the carriers, the geometry of between cesium lead bromide and the carrier. And in this range, we can make nanoparticles which exhibit very bright emission, around 80% in the case of cesium lead bromide. Then on the second step, if we attempt this shelling, so indeed, we don't have merging of nanoparticles, and we still can have a very bright material. We don't change PL peak position in this case, and photoluminescence quantum yield remains nearly the same. What is important during this shelling step, we don't have formation of bulk cesium lead bromide, and this we confirm as absence of bulk emission from cesium lead bromide, which can be observed only at low temperatures. And the most important part is now here in the last two slides. So we can see that this material indeed exhibit much better stability against polar solvents. I can give you a comparison with colloidal particles completely die if we try to wash them with acetonitrile or ethanol or such polar solvents like gamma-butyrolactone, for example. And in contrary, our material can be ultrasonicated in those solvents. But this is only part. So in real life, we need also improve good stability against water. And obviously, sodium bromide is not the ideal shelf if we want to stabilize this material against water. But since we have now a better stability against other polar species, we can encapsulate this material in some polymers, and we can also do in situ polymerization. So we disperse this material in, for example, acrylates and then polymerize. And colloidal particles in this case don't show, so cannot be used. So yeah, with this, I want to thank you for your attention, and I'm sorry for the little bit, I talk a little bit too long. Now, if you have questions, just feel free to ask me.
Okay, thank you very much for the talk. We have a question from our listeners in YouTube, and question from Leonid Dolgov. Dmitry, please say your opinion about it. Some people said that the cheap photovoltaic with low efficiency is better than expensive photovoltaic materials with high efficiency. What is current tendency?
Well, from what I know, it depends what we call cheap and expensive. In reality, for mass production, the state of the art is the silicon-based photovoltaics, and it's already reasonably cheap, just because of the large scale of production. And from what I know, the state of the art actually is not to continue with purely perovskite-based photovoltaics, but to do tandem or even triple solar cells. Then silicon-based chips are or devices represent only one layer, and the second layer is based on lead halide perovskites. So as you may imagine, as you can imagine, this is even more expensive than silicon, but this improves performance of silicon-based solar cells. And this is at the moment considered to be the most interesting devices and most promising.
Okay, thank you. And I have another question which connected with what is the tendency now, what's the situation with problems that lead halide perovskites contains lead, and lead is poisoning. So what is the perspectives of the practical using of perovskites in this sense?
So here I need to split it in two different fields. So in a field of photovoltaics, there are still some debates, but most of the people say that this is not a big issue because it's a green technology, and even for it's a toxic material, but we save environment because we use a very reasonably cheap and good performance solar cells. So, but this is there are still some debates. In the field of luminescent devices based on nanoparticles of lead halide perovskites, it's very different because for those luminescence devices, we need very small amount of those materials. And we are still within, so there are some regulations about the possible lead content, so it has to be below 10,000 ppm. But it turns out that for displays, we need about 100 or 200 ppm only of lead. So it can work. Of course, people still would like to have lead-free material, but at the moment, I think there is a general agreement that it's just not possible. It's really a unique material if we're talking about narrow emission.
Okay, so I think we have to finish. Sorry if not all questions. I think, Elena, do you have
one more question? One more question.
Okay.
Yeah.
Okay, thank you. Thank you.
There is some question from the hall in Lviv, as I understand.
Have you some effort about stabilization and quantization of perovskite nanoparticle in more small porous materials, with a diameter of pore less than 1 nanometer? For example, halide or other.
Let me repeat the question because I'm not sure if I understand correctly. So you are asking if it's possible to stabilize those nanoparticles in small pores, like 1 nanometer.
Possible. Have you some effort?
Have you some effort in this direction?
Yes, so people tried to synthesize those nanoparticles even in cell lights, for example, but in cell lights, the conductivity of pores is challenging because basically this material just cannot go through. So you can not grow, you cannot impregnate cell lights with this material, but there are still some attempts, and there is research that people try to grow nanoparticles, so to grow, for example, moths with this material. So yeah, people try to make extremely small nanoparticles of this.
Thank you. And one more question. Have you some data about defense influence of chemical composition of metals?
Again, if I right understand, you're asking, so how the chemical composition
of metals which you stabilize, right, on optical properties.
So at the moment, the whole field is limited by several by only several compounds. It has to be lead halide perovskite, so lead, but only with chloride, bromide, and iodide. And as A cation, we are limited to cesium, methylammonium, and formamidinium. And all those 9 compounds are considered for many different applications, but in reality, methylammonium-based materials are very unstable, just intrinsically unstable, and cesium and formamidinium are more stable.
Okay, I think we have to stop our discussions. Thank you very much for the interesting talk, interesting answers for the questions.
Thank you.